elements. And in this form, it's actually known for a long time. And it's interesting that it was not really ever connected, to my knowledge, to classical physics. But if you look at this, you just realize that this is nothing but, as we discussed, first-order perturbation theory. So you really study this object when you study perturbation theory, non-degenerate perturbation theory, but degenerate. You secretly study this object because you study how your states change, right? So if you are sort of more advanced, you probably heard about effective theories, Schrieffer-Wolff transformation, renormalization group, or whatever. They are all basis rotation. So it's all about studying these objects. And mostly it was studied perturbatively. But there are lots of issues. Like at some point, you know, you get small denominators and so on. And also because this for few particle systems, you can mostly solve problems exactly, so you don't really care. But when you talk about many particle systems, these matrix elements are super hard to compute. So you all know there are like variational methods to compute ground states and so on. But there are no good methods to consider overlaps. And then what I'm going to also argue today, that it's not enough, at least in many situations, to restrict yourself to few states, like ground state and first excited state. Because there are lots of effects coming from virtual excitations where you have to sum over many energy levels. So that was sort of the reason I spent some time. Today I will go to simpler examples, but if you are interested, you can read more. You can try this variational approach I mentioned and see what it gives you. So basically the bottom, what I wanted to say is that in this form, we say that this is some complicated matrix with some matrix elements related to overlaps between states and so on. But also what I discussed, that it's actually at the same time this AGP is solution of harmless looking equation. Right? Again, it's harmless looking. If you write a simple equation, it doesn't mean there is a simple solution. But in this form, you just see, oh, it's completely basis independent, right? So, and there is an interesting exercise, and if you really want to play with it, I strongly recommend it. So you can just take p squared over 2m plus v of some x and lambda as h. And you can ask for which v this equation has a closed form. Right? It's sort of like usually we solve inverse problems. As I said, that sometimes it's A is very hard to find. You have approximation, but you can ask, can I find a Hamiltonian for which A exists? And I can give you some hints. So you might see that this expression is real. I mean, this Hamiltonian has time reversal symmetry if you are more advanced. So this is imaginary. This is also real. So it means that this term should be also real. At least you are trying to cancel real part and commute with real. So it means that A is imaginary. So actually, you can immediately say that A lambda should have this form. It should be P times some f of x, again, symmetrized. I just don't, it's P times f plus f times P, whatever, plus P cube times G of x, symmetrized, plus so on, right? So in general, it's an infinite series. But you can ask, oh, can I find approximation like this? And this is actually most used approximation in chemistry everywhere. And then actually this problem was solved by Chris Yerzinski and someone, but I really recommend not to look into solution. Try it, it's very simple. And you will find there are only two possibilities. Either f of x is equal to constant, or f of x is proportional to x. One possibility corresponds to translations, another to dilation, squeezing. I will come to that. There is nothing else. So, and then potential should be the form of p of x minus a divided by some constant. So again, I don't want to give you too much. But it becomes more interesting if you add p cubed times some other constant, which is C independent. And then you also ask when I can solve this equation. This was also solved by two Japanese, actually very recently, like 4 years ago, maybe 5, I don't know. Again, I don't want to give you names because I don't want to bias you, but if you're interested, you can find. You will find that solutions are actually solitons of Korteweg equation. So this is equivalent of solving like backscattering problem, and this connects basically adiabatic continuity, locality of adiabatic transformations with actually solitons in water in a very interesting way. So, and I don't think anyone really tried to continue in this series. So you will probably recover some known complicated integrable models in a very simple way. Now, if you use, I don't know, ChatGPT, Mathematica, evaluating these commutators is very simple. So the only thing you have to do is to write consistency conditions. For example, if this commutes with H, you can say that this object should be equal to C plus alpha H plus beta H squared, and so on, right? Because for this simple problem, these are the only objects which commute with H. And then if you match powers of P, you'll find consistency conditions, and they lead to very surprising results. So there is a lot of interesting stuff hiding behind. There is also some interesting stuff which I'll just mention, which is not that relevant to this talk, but it's more like if some of you might be interested. There is very interesting connection to mathematics. As you might see, I'm not really expert in mathematics, but sometimes you bump into truly surprising results. So let me just basically highlight it. And this was actually discovered by Peter Kleiss, who used to work as a postdoc, and now he's moving to a permanent position in Trinity College Dublin. So I also said that formally, this I can continue. This is, as I said, this is your first order perturbation theory. Sorry, I sometimes use psi and sometimes n, it's the same. Anyway, and this we also discussed briefly is the same as 1/2 integral from minus infinity to infinity dt e to the some mu mod t. So mu is a small number, which in principle we should send to 0. And here we have d lambda h of t. And this is my perturbation in Heisenberg representation. So in this way, you just see that for any finite mu, it's defined even for classical system. Because this is just normal time evolution. You observe d lambda h is a function of t. And then from this, I argued that if we do, say, short time expansion, we can expand in Taylor series. We basically can say that my A lambda can be written as sum over k, ck times L 2k plus 1 acting on d lambda h. And Lk means nothing but nested commutator. H, 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 d lambda H, k times. So only odd commutator center. And this is very easy to prove that if you have finite dimensional Hilbert space, that this is exact. So if you have finite, so this coefficient C can be found from this Taylor expansion, and you can integrate and find them. But the point is that this representation is exact. And for some of you who are familiar with sort of recent developments, this is called Krylov space. There is a lot of work now on this. Maybe one last thing I didn't mention, what I want to say is that if we compare this expression and this expression, we actually see that finding adiabatic gauge potential is a problem of polynomial fitting in mathematics. That's again what Peter discovered. It's really surprising where it comes from, but because it's so simple, let me just show it. So let me say that okay, I want to approximate my A with some polynomial, right? This is a polynomial in this nested commutators, Liouvilleans, right? But now I can ask, what will be the matrix element of this polynomial adiabatic gauge potential? And let me add also IH bar here just for the same reasons. Of course, I can absorb them into C's. It's good maybe to write it with I because odd commutators are anti-Hermitian. So if I add I, they explicitly Hermitian. So all my C's must be real. So if I do this, well, what is the matrix element of H and d lambda H? Well, it's very easy to see, right? You can probably see it. In one, H hits this one, gets En. In another, it gets minus Em. So I get En minus Em times d lambda H. Now I add one more commutator. Well, I get another power of En minus Em. So each commutator gives me extra power. So I see that matrix elements of this guy is IH bar sum over K Ck times omega N minus omega M power 2K plus 1 times N d lambda HM. And I just want to highlight, you might ask, why do I do it? Well, these are local operators. Because each time I add a commutator, it becomes a little bit less non-local, right? But if I deal with local Hamiltonian, these are local operators. This who knows what? I have some energy denominator. It's not an operator. It's not written in terms of, say, Pauli matrices of X and P, right? But now let's just look. If we compare into this expression, we just see that all matrix elements of this true A and my, let me call it A star, just to distinguish them, my local A, they actually contain the same matrix element. So it drops out. So as long as I can approximate function 1 over x, which is equal to omega n minus omega m, possible energy differences, with a polynomial of some finite degree, which is dictated by my final term, I'm good. And that's actually a well-known problem in mathematics. People studied it, right? It's clear that if I want to approximate 1 over x with a polynomial, I can only do it in finite window. So, of course, in reality here, I have fixed points, right? These are all possible energy differences. Sometimes I'm only interested in ground state in excitation. So if I do quantum annealing, or if I deal with chemical molecules where electrons follow approximately ground state, there are two, the gaps in molecules are much smaller than KBT typically, right? So then these points will be basically omega n minus omega 0. So if I have few particle system, or like a single spin or whatever, I'll have only 2 points. And actually fitting a polynomial through 2 points is very easy. I need low degree polynomial. So I'll come to that when we discuss simple examples. But if I deal with complicated system, I have very dense spectrum, right? So I can forget about matrix elements. I can say, let me fit a polynomial in the window, right? And now how I choose the window. So, well, highest energy, so I would say highest frequency or highest x in my window is dictated by highest frequency of excitations. So if I have bounded spectrum, like it happens, for example, for non-interacting spins or non-interacting fermions, non-interacting particles, it's very easy. I just set this point as maximal frequency where I can absorb energy, where I have non-zero matrix elements, right? I'm kind of connecting with FGR. And then there is a mathematical result. So if you have polynomial of the order L, this point behaves as 1 over L. So now, if I have a gap, I'm good, because there are no excitations below 1 over L. So I immediately see, if I have a gapped system with finite energy cutoff, I can always do it. So this operator exists, right? Now the question, how do I realize it in the lab, how I approximate it on a computer, and so on, but it exists. If my system is gapless, then it exists only to a certain degree. So these excitations I cannot do anything about them, right? So, and this typically corresponds to a dissipation, Landau-Zener transition. So this part I cannot control, but this part I can control very well. And it becomes more interesting what happens if I have energy absorption at higher and higher frequencies, right? And then you just see if I have higher and higher degree polynomial, it actually introduces larger and larger error in high net frequencies because the verge is stronger. So it actually means that I have to move this point up. And then, again, some of you might know, there were recent papers, I think it's originated in the Hood-Altman group in Berkeley, who they tried to connect it to integrability. I have my own reservations on this. But they basically claimed that if you have generic systems, by generic means local interactions and so on, fermion spins, but with bounded Hilbert space, so it's important. It's like band models, right? It's not XP. Then this tail is exponential. And this tail is nothing but your Fermi-Golden rule rate absorption. Because you ask, remember, Fermi-Golden rule rate is dictated by matrix element squared at high frequency. Well, if you absorb at high frequency. So, and then they concluded that generically it's e to the minus omega with some omega is x. And it turns out that in many classical systems, there is no proof of this, but this works. So you know, like if you have harmonic oscillator, well, harmonic oscillator is trivial, but suppose you have nonlinear oscillator. If you have nonlinear oscillator, then there is always, if you ask what's your spectral contact at high frequencies, right, you will always get some signal because you have periodic motion but not harmonic motion. So if you expand it in Fourier series, you'll have high frequency tails. And these high frequency tails exactly determine your Fermi-Golden rule rate if you talk about quantum language, right? And they're typically also exponential. And it turns out that if it's exponential, you have to move this bound linearly with L. And then it's very interesting. So then if this moves like L and this is 1 over L compared to L, you don't get any gain. So this kind of simple exercise tells you that in order to find good approximation to this operator which generates adiabatic transformations, you want to deal with systems which don't absorb in ultraviolet. It's extremely surprising. But if you think about specific examples, if you think more, you will see, no, it's actually not that surprising. But it's a very interesting connection. Okay, so I think it's all about this. Let me try to move more. And I will say a few words about adiabatic gauge potential in geometry, though I'm not going to talk here about this geometry. It's a very interesting topic, and there is a lot of research, conference, and so on about that. But still, let me just mention it. So in the notion of geometry appeared in 1980, but by the paper Provost and Vallee, who defined quantum geometric tensor. And they define it basically, sometimes it's called Q alpha beta, sometimes G alpha, chi alpha beta, depending on your taste. They define it as basically overlap of some states. Let me just say ground states for concreteness, but it doesn't have to be a ground state. It could be some excited state and so on. But ground state is most used. Psi naught. D beta psi naught. So here, d alpha means d lambda alpha. So now, generally, I can think about my parameter space as a vector space. I have more than one parameter typically, right? Even when we study phase diagrams, we have pressure, volume, magnetic field, and so on. It's the same idea. So these lambda alphas are couplings, physical couplings. And they promote it to a vector space. And then they said, well, is I change coupling, I change the state. State is a vector. There is a natural notion of the distance, right? It just basically tells you how quickly the vector changes, right? So you have one vector, it's your state in the Hilbert space. You have another vector. And then you ask overlap between them, and it's normal, this distance. So it's like 1 minus dot product of these two vectors. And then you expand it to a second order in your deviations, delta lambda. And that's what you find. It's really one-line calculation. But then, up to factors of h bar, this d alpha is the same as a, right? Factor of I doesn't matter because here I get I, here because it's complex conjugate I get minus I, right? So this is the same as n a alpha, a beta, m connected correlation function. Again, sometimes you want to divide by h bar squared, and that's what done usually in sort of quantum information and so on. But I don't want to do it because what I want to argue is that this object is actually physical. That's what you measure in experiments. So if you divide it by h bar squared, then you can do it, but then in all expressions, you will get h bar squared times this. And this will look quantum, but it's not, because classical object is A. So in particular, real part of this tensor is called Fubini study metric. So it's sometimes called G, and this is Q alpha beta plus Q beta alpha over 2. And by the way, this is, of course, a Hermitian matrix in alpha beta space because these are Hermitian operators, right? If you take complex conjugate, it's the same as beta and alpha switch their signs, right? And these are Hermitian operators, so you get G beta alpha. So this real part, this is called Fubini study metric. And don't ask me what it does in math. I am fairly ignorant of this. But what I want to say, this is important. It appears, for example, in quantum Fisher informations, if information for Kramer-Rao bound. So if I don't know if there are any talks, or maybe you heard about this, but basically this would limit sensitivity of any experiments. So if you want to use your state to detect something, time, right? What's the clock? You have atomic, say, clock in Boulder. You have some two-level system of some, I know, cesium. Now they use some other atoms, right? And then you basically have a precession of the spin. It's like superposition of first and two states, the ground and excited, right? The states are highly isolated from anything, so they're very, very stable. And then you measure magnetization, and then by this magnetization precesses, transfers, right? And then you just see how many time sort of it precesses, it gives you time. So that's the idea. So basically you use your wave function to detect time. So when we talk about magnetic field, squids, Josephson effect, it's the same thing, right? We have interference, so the wave function tells you about what is the magnetic flux inside. When you have gravitational detectors, again, same story. You create a beam splitter for particles. One goes higher, one is lower. There is a difference in phase proportional to gravitational field and mass, whatever. And then you detect this, right? And then you can ask how accurate my detectors are. And in a way, this is actually extension of quantum, or generalization of quantum uncertainty principle. So when you measure position, this Kramer-Rao bound reduces to standard uncertainty relation. But anyway, so this G limits your sensitivity. So if you want 1 over G, gives you a bound how accurate you can be. There is some factor of 4. And there is also imaginary part of this. It's called I Q alpha beta minus Q beta alpha, which is the same as minus twice imaginary part of Q alpha beta. And this you might see corresponds to commutator. So this corresponds to anti-commutator of A's, right? Because I have symmetric sum. This corresponds to commutator. And this is nothing but the Berry curvature. So all topology, all whatever is encoded there. Right, quantum Hall effect, topological insulator, and so on. What you mean by alpha beta can depend by on experiments. So very often these are like wave numbers, k, or better, I would say, components of vector potential, because k requires that you have no disorder and so on. But this can be like anything. This can be like on positions, pressure, magnetic fields, so orientation of magnetic field, and so on. And as long as it's non-zero, and this we'll briefly discuss, you will get this non-adiabatic response. So it's basically source of Coriolis-Lorentz forces, always. Again, quantum classically it's the same, but in quantum mechanics you might get quantization. So the fact that you get plateaus in Hall effect, it's of course quantum. The fact that you have response proportional to Berry curvature, Hall response, this is the same. If you have Foucault pendulum, it's Berry curvature which moves it. So, and again, there's a huge amount of literature which secretly studies this object. But mostly they are done through wave functions. And this can be done only in non-interacting cases, or maybe variational cases, like if you have, Laughlin state and so on. And I think it's very interesting to really extend this to interacting systems. So if you can have good variational ansatz for this A and so on. Okay, that's all I wanted to say about geometry. That's, of course, like really a great topic. I want to maybe show some, again, simple example. And hopefully after lunch, I will show a bit harder examples, but then I show you like pictures, I show you slides, because those, it takes a bit longer to derive. So let me go back to a very simple system when I have particle in a magnetic field. I'm slowly going to this originally advertised example where we'll later add momentum. But now I just want to study geometry. And let me just say, for simplicity, magnetic field will only contain Z and X component. Again, it doesn't really matter, but it just simplifies algebra a little bit. So let me try to compute adiabatic gauge potential with respect to theta. Right? And then you will see immediately how many things I told you work together. So I have two states. Say ground state. This will be cosine theta over 2 sine theta over 2. Assume you all know it. When theta equals to 0, it's 1, 0, right? When theta is equal to pi, then pi over 2, right? When theta is equal to pi over 2, my ground state should be along x, and that's exactly 1 over square root of 2, 1 over square root of 2. And excited state will be, of course, orthogonal to it. Okay, so now let me find, so this system is so simple that I can find adiabatic gauge potential by just differentiating states. It's 2 by 2 matrix, right? So let me find I h bar d by d theta acting on the ground state. I'll just do this exercise, right? So what is this? It's equal to I h bar over 2, right? I get 1/2 because I have half argument. And then I will get minus sine theta over 2 cosine theta over 2, right? And this is what? It's minus I h bar over 2 times excited state. So let me now do the same for the excited state, the E. So I will get again I h bar over 2, and here we get cosine theta over 2, sine theta over 2, right? So here minus will become plus, and this is nothing but I h bar over 2 times the ground state. Right? So now I can immediately see what this operator IH bar d by d theta as a matrix. This is nothing but sigma y, right? So I can conclude that A theta will be equal to H bar over 2 times sigma y, which is the same as Sy over 2. Sorry, Sy without over 2. I'm just saying it's just Sy. Right. So, and this is what I was saying. Generator of rotations in XZ plane is Sy. We know it, right? So you just see how it works. But you can immediately see that you can get it from this equation right away. I just told you that I can get it from commutator expansion. And moreover, well, this picture I erased, I have only one point, one gap. So it basically means I can approximate it with one commutator. I just need to find a line polynomial which goes to one point. So let me just check what this commutator is. So I need to compute commutator, I said, of H and d theta H, right? Now, H contains SZ and SX. D theta H also contains SZ and SX. So this commutator is proportional to Sy, right? Now I can say, what is the coefficient? Well, I can either, in this case it's simple enough, try to find it such that this equation is satisfied, or I can use variational minimization, which I mentioned. Both results give you exactly this coefficient 1. It's very easy exercise. I just don't want to spend my time. So we see in this case, adiabatic gauge potential is very simple. So if you have two spins, it's also a good exercise. So suppose you have some ZZ interaction, right? So if your H will contain also, or just some S1 or S2 is be anything. So then you will also get some two-spin terms. But again, you will get exact result. And moreover, you know that if you are interested in AGP from the ground state, you can stop at third commutator at second because you have only two gaps from the ground state. So it actually means that you need one more order in a polynomial to fit it. So you know in advance that if you add third commutator, you will cover it. So your AGP just contains two coefficients. But if you go to more and more spins, exact AGP generally becomes more and more complicated unless your problem is simple, like integrable. If you have transversal Ising model or something like that, you cannot still do it. But if it's non-integrable, you have to do approximations. Okay. So now, let me go to what we also started discussing last time. I will go to the moving frame. So remember what we discussed, that if I expand my state in this basis, where theta depends on time, that's exactly what happens when I'm going to a moving frame, right? I'm not expanding in the original, say, lab basis, right, where the theta is fixed, but in time-dependent basis. Then we substitute this, so I just write my psi, and I remind you it's AG times psi g plus A excited, psi excited, whatever, right? So normally when you solve Schrodinger equation, I guess probably 99% of your time, or maybe even 100% of the time, you discuss fixed basis. By the way, psychologically, it's extremely interesting. When you learn classical mechanics, you discuss moving frame. When you learn quantum, it doesn't exist. Why? When you learn quantum mechanics, you discuss stationary states. When you learn classical mechanics, you never discuss stationary probability distributions. Why? It's very interesting. I mean, of course, it's historical, because quantum mechanics was invented for hydrogen, whatever, for atomic states, and classical mechanics for soccer balls. But as we progress, actually, it's in order to understand what is quantum, what is classical, I'm coming back to Jamir was teasing me, you really have to first bring everything to the same language. Anyway, so here, I'm partly closing this gap, right? So what we discussed last time, that if you go to a basis which is time dependent, then when you plug into Schrodinger equation, you will get two contributions. One that you differentiate these coefficients, and another that you differentiate the states. But the states only implicitly depend on time, right, through theta. So I can use a chain rule. And then the second contribution, I can move to the right-hand side, say, it's actually part of my Hamiltonian. But then when I define time derivative, I call it moving time derivative. It's actually time derivative which only acts on these coefficients. So for example, if I follow adiabatically my state, moving time derivative must be 0. And here we immediately recover adiabatic theorem. It's in one line, don't need to write anything, gaps or whatever. You just see that when lambda dot goes to 0, well, theta dot in this case, this term is not important. But h acting on this size returns me a number, right? So there are no transitions. So these coefficients, my a's only acquire phase, right? Because there are no off-diagonal matrix elements. So I immediately say, yes, this is a proof of a adiabatic theorem in one line. It actually works for classical systems as well, right? With caveat that A can be singular. But if you have a simple system, you know, if you slowly squeeze in your piston and then unsqueezing it, nothing happens. It's thermodynamic adiabaticity. It's actually contained there, right? Because again, this is quantum or classical. Anyway, so now let's go back. And then I can work in, actually, as I said, once you write this equation, you can work in any basis. It doesn't matter. It's always basis invariant, right? This moving time derivative, of course, knows about the basis, but that's already absorbed. But let me indeed go to the basis which co-moves with magnetic field. It's convenient. Then my H will be just B times SZ, right? Because I chose my axis along B. I don't have to do it. I just want to highlight. I can work in any basis. But this is sort of, it is convenient. And then if I do rotation in XZ plane, my sigma y is still sigma y. It doesn't care because it still does this rotation. So you get minus theta dot, I guess it's minus, times Sy, right? And this we call moving Hamiltonian. So, and now you kind of see how these words I was saying are realized, right? So you create effective magnetic field along y direction. And this you know very well, right? When you go to rotating frame, it's as if you have a magnetic field. Conversely, if you have a magnetic field, you can go to rotating frame to cancel it. It's completely equivalent, right? So this extra magnetic field, this is your fictitious force, right? That's I mean, it's a source of the force. It's a Hamiltonian. It's a source of all these Coriolis and so on forces, right? So, and then you see again a adiabatic theorem, right? So if your theta dot is 0, your moving Hamiltonian is just as Z, right? But unlike stationary states, it's actually rotating B, right? Because I'm working in co-moving basis. So I am following ground state of rotating Hamiltonian. Okay. So now, before I conclude, let me just say a few words about adiabatic perturbation theory. And I think it's interesting because we will be able to connect geometry and non-adiabatic response. I said there are like thousands of papers, or hundreds, I don't know, studying geometry now. Of course, it's known in many contexts that non-adiabatic response is geometric, like quantum Hall effect I mentioned. But it's much less known that actually inertia mass, so the mass which you see, the mass of the brick when I throw, is also highly geometric. And this is something I want to discuss. So if you think about an example, so here the mass analog of mass is, of course, moment of inertia. But for the pictorial purposes, let me just go back to more simple situation. I have, for example, mass of the box, and I have little mass of the particle inside. So let's just think conceptually why the mass of the box changes. And again, back box is your atom, little mass is your electron, right? Of course, we all know that in this situation, my total mass is m plus m, right? So, and we better recover it from this, because if we don't, then we do something incorrectly. But let me just say in the beginning, from the beginning, let's just think where this little m comes from, right? So usually we're saying that sort of they move together, center of mass, I don't know. But let me just think sort of conceptually from the point of view of adiabatic perturbation theory, right? So what happens? When I move, there is extra fictitious force, inertia, which creates extra pressure, right? And this extra pressure is picked up by this force. You have to fight this extra pressure, right? And that's why it becomes heavier. So if I think about quantum language, what happens is that because of fictitious forces, this particle does not follow instantaneous ground state. Because in instantaneous ground state, particle is not moving, right? In instantaneous ground state, expectation value of momentum is 0. So that's exactly what Born-Oppenheimer approximation misses. But we know that actually this particle should be moving. It should have extra momentum. So it basically means that its state is not the ground state. It's excited somewhat, right? So now let's try to do perturbation theory. So my h moving is h minus lambda dot a lambda. And in this case, a lambda is just p, right? We discussed, because I'm translating. General rate of translations is p. But I just want to be general. Now, I mentioned that in the limit lambda dot goes to 0, you just follow the ground state of this. But now I can ask, what's the next correction? And in principle, you can just do standard time-dependent perturbation theory. You just say, let me assume that you start slowly. Again, if you don't start slowly, you will create some transients, and you know very well, if train starts moving suddenly, your water will start splashing, right? So, but if you want to get extra mass, you can say, okay, let's accelerate train slowly, and let's see what kind of extra mass. Again, it's not really important, but once you do calculations, you have to think about these things, because you might get an answer which will be correct, but then you have to interpret where this extra stuff comes from. But I would say there is actually a much simpler way to solve it. What I will say, okay, in the next order, actually my system will follow ground state of this Hamiltonian. Why? Because I can now apply a adiabatic theorem to this guy. And now I can do the same thing. I can define a adiabatic gauge potential to this Hamiltonian, right? Go to a moving frame. And then I will get something like lambda double dot times b lambda plus lambda dot squared times whatever c lambda and so on. I'll get this. And these are known as super adiabatic terms. Like Beriev was first who discovered it. And then you just see up to higher order. So lambda double dot, in a way, is also small, because when you do a adiabatic approximation, your small parameter is 1 over total time, right? If you want to formally define small parameter, you just say you have some path. Say train goes from São Paulo to Rio. There are no trains here, right? Bus, okay. Bus goes from São Paulo to Rio. And then you're saying, let's consider this more adiabatic bus, which does exact same thing, but 2 times slower, right? And then your adiabatic parameter is 1 over time, right? So, and then lambda double dot is 1 over time squared, and lambda dot squared is 1 over time squared. Again, this is a way to organize series, right? When we do any perturbation theory, we have to do small parameters. Okay, so when we organize series in this way, we just see that up to terms which have 1 over t squared, we actually follow ground state of this guy. Because now I'm repeating same adiabatic theorem to this guy, right? Again, I'm just saving my time. If you are not convinced, just do normal perturbation theory with this guy, and you'll get same results. If you are interested, I can send you details of the derivation. It's not that hard, but it's a little bit longer. But if I convinced you that we follow ground state of calculation is trivial, because I can use static perturbations. I can say that my psi moving, again, let's say I follow the ground state. It's not important. Could be instead of 0, could be 1, 2, 3, and so on. Right? So what is psi moving 0? It's just psi 0, right? And then I have to add this perturbation. I have to be careful with signs. But you know, I just use normal perturbations here. It's minus lambda dot times sum over m not equal to 0, right? Sum of all excited states. And I have psi m, a lambda, psi 0, divided by em minus e0 times psi m. Again, I'm not 100% confident about sign, but you can look in the notes. But anyway, sign is the same as in your standard perturbation theory. So whatever it is there, you use the same expression here. Okay. So this is psi m 0. So I see that because of that fictitious term, actually my state, as I was saying, it does not really follow the ground state. Now I can ask, what is my energy? So I ask, what is expectation value of H in this ground state? My energy, remember, this is fictitious transformation. Energy is still energy. It's average of the Hamiltonian, right? When we do frame transformations, we just sort of, we interpret some terms in one way, some in another, so we solve Schrodinger equation in a different way. But when we compute observables, it's normal quantum mechanics, right? Nothing in it. It's still average of H is energy, average of X is mean position, average of P, and so on, right? So, but what I'm using that my ground state of a moving Hamiltonian is not the same as the ground state of static Hamiltonian. And now, if you stare at this, you immediately realize that because H is diagonal, there is no linear order correction. That's a standard result of perturbations. Again, it just comes from the fact that if instead of psi m naught, I will write this first order correction, but instead of psi m naught on the left-hand side, psi naught, then H acting on this will give me naught, and the rest part is orthogonal, right? So next order correction is lambda dot squared, right? This looks something familiar, right? We should get extra energy proportional to velocity squared, right? What is left inside? Well, let me just say it in words. You get square of this guy. So I'll get EM minus E0 squared. Then you have to multiply it by EM, because I compute this, right? But then you might remember, then when I do first order correction squared, I have to take into account normalization of my wave function, right? Remember, second order correction to the wave function is given by sum of first order corrections squared, right? And this will give me minus E naught, because you'll get minus 1/2 if you remember perturbation theory. You'll get minus 1/2 here, minus 1/2 here. Again, so what will happen, but you can say it's also invariant. Only energy differences can enter. So basically what will happen, instead of EM, you'll get EM minus E0. So you will get EM minus E0 squared from squaring perturbation, and you get EM minus E0 power 1 because you compute average Hamiltonian. If you compute energy variance, you cancel it exactly, and you will get exactly metric tensor. But here you will get what? Psi m, a lambda 0, 0, a lambda psi m over em minus E0. So if your lambda has components, then exact same analysis will give you this. But this I want to rewrite as lambda alpha dot, lambda beta dot over 2 times, I call it kappa alpha beta, just not to confuse with summation indices m, but basically this will be a definition of my mass tensor. If I have one parameter, it's just a mass. And then you see that kappa alpha beta is equal to sum of m, I'll save notations, will not write psi, a lambda 0, 0, a alpha, a beta, m. Kappa alpha beta is, of course, symmetric tensor because I sum over alpha and beta. So whenever I switch them, it's only symmetric part which enters anyway. So I can write plus alpha change beta. And I write em minus E0. And I guess I get 2 if I do everything correctly. Yeah, I get 1/2 from here, but I also here get 1/2 from symmetrization. Anyway, this should work. So you see, this is almost quantum geometric tensor. I have extra energy denominator. And there are some bounds, for example, very recently, Liang Fu put bound on basically relation of the mass and conductivity. So this bound will be that for the ground state, I can write it's less or equal than geometric tensor over gap, right? So that's basically implicitly, he didn't use this language, but that's implicitly what he used in the derivation. And this was applied to band structures. But I just want to highlight this always works. But we can actually see a relation with geometric tensor a bit closer if we say, what if my particle here is not in the ground state, but in some Gibbs state? And of course, there could be many particles. Then I can just generalize it. So I'll get that kappa alpha beta will be sum over n, rho n. I basically weight initial state with rho n. Instead of a ground state, I will say with probability rho n, I have the state n. And I have n, a beta m plus alpha plus beta over 2 em minus en. Actually, check this too, because no, there is no 2 here. I apologize. Anyway, I don't want to check it now. Yeah, because this 2 is absorbed by this extra guy. It doesn't matter. So, yeah, there is no 2. But then, you know, if you see sums like that, you probably know there is immediate desire to anti-symmetrize. You basically, you see, if you exchange n and m, these guys are almost the same, right? So it means I split the sum into 2 identical sums, and in one I replace index n and index m, right? So this guy will be the same. It's completely symmetric. So this will not change. This will change sign. And here rho n will become minus rho m for this reason. So I'll get double sum, and this is, of course, sum over m not equal to n. I forgot. It's a double sum over n not equal to m, rho n minus rho m times em minus en times m, a alpha n, a beta m plus alpha beta. And now I have 1/2 because I did anti-symmetrization. So now 1/2 appeared, right? I split my sum into 2. But now let's just look into Gibbs ensemble. It's the most important. If rho n is equal to e to the minus beta en, then 1 over z, of course, then rho n minus rho m will be 1 over z times e to the minus beta en. And here I get e to the minus e beta em minus en. And now I just see that if I have high temperature limit, again, high temperature is determined by your physics, but so here high temperature will be larger than level spacing. Then I can expand this, and em minus en changes, it cancels. So from here I get very interesting result that in high temperature, or classical limit, by the way, When I talk about classical limit, energy difference scale is h bar. So also by dimensional analysis. So when either I take classical limit, and here you kind of see classical limit means I go to very high states, high temperature limit means the same thing. So kappa alpha beta will be B beta times G alpha beta. So in the classical limit, there is a direct relation. So basically the extra mass you pick up, so if you have, say, polaron, or you have some rotating spin, or you have a superconductor. There were actually very nice recent works by Päivi Torma about connecting superfluid density and geometry. They are all contained in this expression. So this extra mass which you get is the geometric tensor. So when you're quantum, this relation is a little bit more subtle. I just said it doesn't work, but you can almost see that if you differentiate this with respect to beta, you gain a geometric tensor. So more generally, it's actually derivative of the mass with respect to temperature is related to geometric tensor. Let me go again to a simple example, but now I will use this box because it's more familiar. So then you can ask, what are you talking about? So my mass is mass, it's temperature independent. Well, you can immediately imagine that this is a very special case, because when I even deal with polaron or whatever, superfluidity, my superfluid density doesn't know about temperature. But here, this example is very simple. So what I'm telling you, I don't need to put indices, it's one-dimensional parameter space. I just told you that kappa is equal to sum over, let's say, kappa n for state n, sum over m not equal to n, m p n p m divided by en minus em, where p is momentum. I told you. And you can do your favorite examples, square well potential, harmonic oscillator, or whatever, and you will get that it's exactly little m. Sorry, it's not summation index, it's this mass. So in this case, you just recover what I told you, and this, if you look at this, it's actually highly non-trivial sum rule. So it has to work, because at the end you can prove this result by boost by Galilean invariance, as you usually do in classical physics, right? But you formally recover it from perturbation theory. And as I said, this extra correction, so this kappa doesn't depend on n, and for this reason doesn't depend on temperature. It's always mass. But I can give you another very interesting example. So suppose now we have a piston. So it's the same setup, but so this example you saw in ideal gases, but assume that only one wall can move, right? So it has mass m, but there is a particle, or could be many particles with little mass m. And I can ask you the same question. You do experiment, what is the mass of the piston? And I think unless you read about this already, you will not guess right. You kind of see how it works, right? If two walls move, it's trivial. If one wall moves, yeah, I should pick up some contribution. But what is it? Is it m over 2 because I have one wall? Is it 0? Is it still m? So it turns out, when I tried this problem quantum mechanically, it's actually, again, two-line calculation. But then I was curious. I had like long time from Europe. I thought, let me derive it classically. So classically, I have a particle which is moving, but also piston accelerating, trying to find extra kinetic. It took me 5 hours to do this calculation. It's extremely subtle, because each time I was getting wrong answer, I already knew the correct answer. And then I said, oh, I forgot this term, because you really have to be careful. You should not miss any single correction. Because the idea that, of course, single particle, you just have collisions, but you have to be careful. Collision depends on instantaneous velocity of this, and this knows about acceleration. That's actually how you get extra force or extra kinetic energy. Extra force knows about acceleration, kinetic energy knows about velocity. let me just maybe flash you an answer and say that this could be already very non-trivial here. So if I ask, what is the diabatic gauge potential? Well, it's very simple. My eigenstates, psi, so let me call it this position L. It's more familiar. My psi n, let's say it's a square well potential. So I get some psi n of x over L, right? These are my dimensionless wave functions, right? So this is what we do. And this psi n will be sine pi n x. So it's really like first class on undergraduate physics. But probably you don't know what's the derivative operator, right? You, I assume, never saw this calculation. I ask, what is the derivative of this? And it's actually, again, very simple calculation. So I will get, is I differentiate L, square root of L, I get extra 1/2 minus and 1 over L compared to psi. So I can write it's minus IH bar over L times psi n, right? So this is the first term which comes from differentiating L. But then there is another term. What is this? I get again minus, because 1 over L will give me 1 over L squared, right? And then I will get a factor x over L. But I can write it in the following way. It's minus IH bar over L times x times d by dx acting on psi n. Right? So you see, d by dx acting on psi n will also give me psi prime, but it gives me 1 over L. When I act d by dl, I will get psi prime, but I also get x over L squared. So I get extra L and extra x. So, but this is nothing but P. So I get Px, and then I get extra IH bar over 2, sorry. And if you do careful work, you just see this is what I was trying to say. You get sometimes i's because you have non-Hermitian operators. If you symmetrize, you will get that's exactly equal to this. So, and this is, 2L, sorry, 2L. So, and this is what's known as dilation operator, x times p, right? It's p translates you, but it translates to by amount proportional to x. That's what you dilate, right? And now, I leave it up to you if you are interested. You can just evaluate this using d instead of p. And you'll find a very interesting result. Then kappa, and so this extra mass will be m over 3 times 1 minus 3 over 2 by squared n squared. So this extra mass will be 1/3 of the mass of the particle, and moreover, you'll get extra anomalous quantum correction. So in the classical limit, which you can also get in high temperature limit, it's just m over 3, and this is geometric tensor. You can see immediately where it comes from. I said geometric tensor is px in the classical limit. Average of x squared is 1/3. So that's 1/3. It's the same origin as geometric tensor. And if I ask you what this m over 3 is, I don't know, can anyone tell me what is the object which has mass m over 3? Does anyone know? It's a very, very familiar object. I can tell you. It's an elastic spring. Because you, of course, see elastic springs in millions of problems, but they always say, let's assume it's massless. But what if not? What your elastic spring has a mass? Which kind of mass you will get if you move only one end of the spring? Well, velocity is proportional to displacement, right? So your mass, your kinetic energy density will be rho x dot squared over 2. Rho is constant approximately, if you have small oscillations, right? But x dot is proportional to x. So if you average kinetic energy, you'll get 1/3. So it basically means that if you want to discuss this very, very familiar object, right? You have a spring and the mass, It's like high school student, high school problem, and you ask what's this acceleration or whatever. But if you say that mass of the spring is non-zero, then actually in your Newton's equations you will need to have 1/3. And this 1/3, as I tried to convince you, has quantum geometric origin. And maybe you can now see why I wanted to avoid word quantum. Because here, this part is quantum. Actually, deviation from 1/3 is quantum. And it's interesting, now you can do the same exercise with photon gas, and you will pick up Casimir energy, exactly, and you will get similar anomalous correction. You'll get Casimir energy over 3 for dilations and Casimir energy for translations. So from this formalism, you actually recover what you expect, that even if you drag vacuum, you become heavier. Okay. So I still want to tell you, I think, interesting stuff. So let me maybe skip curvature part. Let me just say in words. So if you want to now compute in the same way, using perturbation theory, response of some operator, we can call it d lambda h. It's conjugate to some parameter that you will find in the leading order perturbation theory, just linear response with respect to this boost term. You will see that, of course, it will be d lambda h naught minus f alpha beta times lambda beta dot, where f will be a Berry curvature. It will be anti-commutator. And this is exactly, if you want to think classically, that's your Coriolis force, because lambda beta could be angle of the Earth. So lambda beta dot will be your omega. This will be your Berry curvature, which is non-zero, just not quantized classically. This will be anyway, you'll get the standard expression. There will be some sine theta. Already forgot. It's large on pole. It's small on the equator, right? So you will get this geometric contribution. But if you think about lambda beta as, say, vector potential, say, I'll call it lambda x and lambda y, then derivative of the vector potential is what? Electric field. dH vector potential is what? It's current. So you get Jy is equal to Berry curvature times electric field along x. And then what you probably know, and what I'm not going to discuss, integral of the Berry curvature generally gives you an integer. So this is a quantum result, because classically you typically average over many states. For each state you have your own integer. When you average, you get a continuous number. So quantum effect here is that this generally Chern number, but if Chern number doesn't depend on vector potential, Berry curvature itself is quantized. And then you can get quantum Hall effect. Okay. So I really want to start with my motivation and go back to this, right? So now I want to combine these two topics, which I discussed. I want to somehow treat P and X as classical numbers. And again, I just want to say this is at the end not important, because I'm going to do Wigner-Weil transform. You can always go back, do inverse Wigner-Weil transform. So I only say they're classical for intuition, because I'm going to show you pictures, and then you can visualize the pictures, what particle is doing, right? Because when I talk about operators, it's much harder to think. We have to think about some expectation values and so on. And I want to think about spin as a quantum. And then I already, I guess, convinced you how it's related to adiabatic transformation. The idea is that my classical degree is slow, my spin is fast, so it almost follows this x, right? But then it almost does a adiabatic transformation. And then I kind of already told you, you should get some extra forces compared to Born-Oppenheimer, right? You could pick mass, Coriolis force, and so on. But now let me tell you where the difficulty is and how Bernardo solved it. So in reality, of course, I talked very little about this, but I kind of mentioned in the end how I want to convert p and x into classical variables. Well, or justify this. How to convert, I told you. You just do Wigner transform or Weyl transform. How I justify it? Well, I justify it through path integral because I get this very complicated star product with exponentials, which I don't know what to do with. Of course, I can say, let's assume it's classical. Yeah, I can always do it. But if you ask me how good your assumption is, you have to have some handle how to evaluate it, right? So path integral gives you this handle. So you can find a saddle point, and you can study correction. And let me say where the difficulties are and why this problem was not solved for so long. You will not find it in any textbook. I mean, there are actually some textbooks like Shankar which discuss some perturbative limits of this, so I'm not, it's not that, of course, people kind of know, they do experiments with this, but you will not find a clean derivation of what's going on in textbook for this trivial problem, right? It's just, we discuss particles, we discuss spin. For particles with spin, we say, oh, there is a Stern-Gerlach experiment where actually B is fixed direction, and we say, they go to the left, other particles go to the right without even saying why, right? And then we move on, right? So in all the courses, I would say, at least all I know, we either discuss spins or particles, but we never merge them together. But of course, in reality, they move together, right? Of course, when you go to many-body systems, then people do various perturbative methods and so on and so forth. But before you do this, I think it's good to understand this very simple problem, right? And actually, I told you, like Steve Gervin mentioned it to me when I was graduating, I didn't know how to solve this problem for like also many years. And luckily, Bernardo figured out how to do it. So let me just say kind of what's the, where the difficulties are. So suppose I want to write my path integral. So I just said I write, again, I write the whole thing, right, with ht over h bar, there's operators and so on. And then I start inserting the states, right? But I don't want to treat spins classically. I want to keep them as operators. So it actually means that when you start inserting states, you add xi up, xi up, then you have 1 plus I delta ht over h bar. Then you might maybe add pi up, pi up. Then you will also add to this xi down, right? So I have to resolve identity. Now, in order to resolve identity, it's not enough to just add x position states. I have to add spins. So spins are my internal quantum degrees of freedom. So actually what I get is sort of some extra sums over quantum indices. And this Hamiltonian, it becomes a matrix, right? It generally couples different states, say up and down, right? And now it's matrix only in spin space because x and p are converted to numbers. I have path integral in x and p space, matrix in spin space. And now I want to take a saddle point of these products of exponents, products of matrices. I don't know how to do it. What is the saddle point if we have product of matrices? The only way to do it, known to me at least, is that you convert the spins to also classical variables. You write spin path integral. But that's, I don't want to do it. Because for spins, I cannot take saddle points. Spins are quantum. So what people then said, no, let's not look into up and down bases. Let's look into states which diagonalize H at given B. I don't know how I call it. Let me call chi up, or chi B up. I don't know how I call it. So it will be up state along B, right? I still resolve identity, right? There is no problem. I have up and down. And now look, this guy is diagonal. I get product of numbers. When I get diagonal matrices, my each eigenstate is basically classical. That's actually how you justify Born-Oppenheimer from path integral. You just say, for each state, you have your own diagonal matrix, and then we do standard stuff. It's just each internal state, ground spin state has its life, excited, its life. Exactly like Stern-Gerlach experiment, right? Up state goes to the right, left state goes to the left. They both described by classical physics, just different Hamiltonians, right? But the problem actually got simpler, but it didn't disappear. Because next guy, I'll get maybe something. Let me just ignore P. P you can insert later to resolve identity. Let me just write X. So I have X I plus 1, and then I will get chi B up, chi B down, right? I do the same thing. But now I have a problem because, yes, H is diagonal, but this chi is not the same as this chi because my basis changed. So now my problem is still a matrix problem. I just converted difficulty from Hamiltonian, which is diagonal, to overlap of states. And then what is tempting to do is to say that, well, we take a saddle point, but because X, say, changes smoothly, right, it's classical, I will actually get this extra contribution which we just discussed, at least to the leading order. I get B of X times S, I put hat. Here I don't put hats, I just said we converted it. So this becomes X of T, right? When I do path integral, this becomes P of T, X of T. It's like I kind of go to Heisenberg picture with respect to X and P, right? But I still keep Schrodinger picture here. And then I will get my adiabatic gauge potential times X dot. So that's extremely tempting, but it's also not right. So first of all, and this actually we spent, believe it or not, 1 year trying to understand what to do with this. You can ask, wait, but what is this? So, well, then of course I can say that I will follow up and down states of this guy, and average of this will be my classical Hamiltonian. But then you immediately ask the question, and you can ask the question, what does it mean? Hamiltonian should depend on momentum. Here have velocity and momentum. Maybe it's Lagrangian, but Lagrangian should depend on X dot, not on P. So what do I do? There's clearly something missing, but there is also something else is missing. I told you that when we do just perturbation theory, that's what people do. If you remember, I mentioned there is a Born-Juan correction, which is A squared. This just disappeared. It doesn't exist. Right? Remember, A squared was coming from P squared acting on my whatever spinors, right? It's non-path integral way of deriving this. We just postulate that we follow the ground state, and we get basically A squared for first derivative. This term is gone. So I will tell you where the mistake is, and next time I will explain the solution, and then I'll show you the slides, and I hope I will convince you that the results are really extremely unintuitive and super interesting. At least this is how I view it. Mistake is that actually when you take path integral, and this I explained a little bit, it's not X which is continuous. That's not true. What is continuous is X forward plus X backward. This is your classical X. But remember, I told there is also quantum part of X, which is X forward minus X backward. And over this, you integrate. This is what gives you delta function. This is what gives you a constraint. So it actually means I cannot say, so this is only forward parse. At this level, I cannot convert this to a smooth number. And if it's a not smooth number, I cannot write this. Because what is X dot if it jumps from point to point? X dot is only defined if I'm dealing with something continuous. So there is, if you want, quantum noise. And this A squared term really comes from noise. And how to include this noise, we thought for a long time. We already knew the answer. We, of course, wanted to see how this answer goes if you go beyond this perturbative limit and so on. And then actually Bernardo found an extremely elegant solution, which I'll probably discuss after the lunch break. Okay. Any questions, comments? You should ask more questions. I don't know if you lost me, if it's too complicated, just you should stop me. Anyway, I hope that I will connect it to physics and then forget about the math. I'll show you pictures and maybe you'll appreciate that. That's interesting. But it's amazing. This stuff was completely missed by many people, like by Berry, by Wilczek, by like everyone. So it's amazing. I'm pretty sure you will find some analogies in high energy physics. When I mean missed, I mean not for specific problems, but generally. So, and people only now kind of rediscover these things. Yes.
In a quantum formulation, how do you feel, or how do you realize that you're in a moving frame?
Oh, that's exactly what. Let me start. I will promise. I'll answer. You're not leaving right now, right? I will start next lecture answering this, and the answer is, like, to me, it's like most amazing. So I think it's fair for me to say it because Bernardo found it, so I'm not prizing myself. He just discovered it. Yes, you realize it. I can tell you through Moyle product. Moyle product knows about moving frames. So the stuff I was like loading and I'm going to use and show, like, yes, it knows about dynamics, and I will try to convince you that even thermodynamics knows about motion and so on. It's extremely interesting, actually. Yes, Moyle product knows about this. You don't need any equations of motion. Okay, then maybe I suggest that we have a lunch break now, and we meet at 2:30, right?